to get started? Okay. Okay, so now in the previous lecture, I told you that our knowledge of the weak interactions is basically perfect. In particular, for the Z boson, we write down this particular set of charges, and we have this universal coupling that goes in front of it. And from that, we can predict all the properties of the Z boson to high accuracy. So this is a triumph. But now, as I said before, when you learn something at a certain layer of knowledge, then you always have to ask below it, do I understand the foundations of that? And I think here we can go one level deeper before we really run into problems. So this is what I want to do in this lecture, discuss this point. Now, you could legitimately ask the following question about the previous lecture. Okay, you showed me that this formula is correct. But maybe I don't need the whole structure of a gauge theory in order to get this formula. In particular, the spontaneously broken gauge theory, the idea of spontaneous symmetry breaking, is a kind of complicated concept. Maybe I can get this formula without that. And to do that, I would just postulate this formula for the couplings, and I'd just postulate that the Z and W get mass, and then go ahead and calculate, and I could have gotten all the predictions that I had in the previous slide. So why do we have to take seriously that this is a gauge theory and that it has spontaneous symmetry breaking? So let's talk about that a little. So first of all, there is just something in the universality of couplings which requires that you take the gauge theory structure seriously. And this is because coupling constants in quantum field theory are renormalized. So you can have two coupling constants that are equal, you set them equal, but then if you evaluate them at a different scale, a different momentum scale, they could become separated. So for example, if I have a lepton and a quark, to go find my pen set right. If I have a lepton and a quark that couple to the Z, and I write the formula for QZ at this vertex, okay, well look, this diagram can get corrected by QCD. And this diagram does not get corrected by QCD. So you might expect that at any different scale, the relation between these two constants would be broken. And for example, this would be a larger coupling in general than this one. So why is it that the couplings of the weak interactions are so universal? And I think if you're familiar with quantum electrodynamics, you know the answer to this question. It is true in quantum electrodynamics, and it'll be true in any gauge theory, that in a gauge theory, there's a conserved current here. The conserved current has a ward identity that tells you in QED the formula Z1 equals Z2. It protects that current from having its strength renormalized. And so no matter how complicated are the interactions here, they're going to cancel between diagrams like this and, for example, diagrams like this, because of, oh, sorry. I meant to write a diagram like this with the self-energy. Because of the word identities of the gauge theory. And so as long as we have a gauge theory with conserved currents, we're protected from this non-universality. We have couplings that are universal. And I think in quantum field theory, there's no other good explanation of why coupling should be universal. So already that's something that you should take a little seriously if you want to challenge the idea that the weak interactions are a gauge theory. But there's another piece of this story, which is actually more interesting. It's even a little stranger. And that has to do with the physics of the massive vector boson. A massive vector boson is really different from a massless vector boson. And you can see that already in the degree of freedom counting. The photon is a massless vector boson. You find its degrees of freedom by solving Maxwell's equations. You find that the solutions of Maxwell's equations travel at the speed of light, and they have two polarization states, namely the two directions orthogonal to the direction of motion. Linear combinations are the left-handed spinning and right-handed spinning photon. However, a massive vector boson has three polarization states. And the reason you know that is because you can always, if it's massive, you can always boost to a frame where it's at rest. You can't do that for a massless particle, but for a massive particle you can do that. And then you can rotate its polarization vector into any orientation in that frame using ordinary rotations. And so if it's a spin 1 particle, you can access any of the three states that are available as polarization states of a spin 1 particle. So first of all, 2 degrees of freedom, 3 degrees of freedom. So they're really different animals. One can ask, where did this extra degree of freedom come from? In the standard model, it comes because when the vector boson gets massed through the Higgs mechanism, it absorbs the Goldstone boson from the Higgs sector, or from whatever entity it is that spontaneously breaks the symmetry. But now things get a little weirder, and let me explain that. So here are the 3 polarization states written in some preferred basis. These are the ones we had before, and this is the new one. This is in the rest frame of the W boson, let's say. But now let me take these 4 vectors and let me boost them in the 3 direction, corresponding to a boosted W boson. Of course, these vectors are transverse to the boost, so they're not changed, but this vector is along the boost, and so it's actually going to get changed. And so when you do that, what you get are the vectors on the next slide. So this is the same as we had before, but this one is different. That's just the simple consequence of boosting the vector 0, 0, 0, 1. Okay. Well, look at this. The components of this vector are growing without bound as the W boson is boosted. In fact, it approaches p mu over m. So it actually becomes parallel to the momentum vector of the W boson. Now be careful, it's still orthogonal to the momentum vector of the W boson in the sense that epsilon 0 dot p is always equal to 0. But nevertheless, it becomes parallel to it. That's a funny thing about Minkowski geometry. But these large numbers here might cause us some trouble. And I'll give you some specific examples as we go forward. Another way to express this is the polarization sum, this quantity here. In the rest frame, that would be g mu nu minus something that projects out the time-like polarization. If you write that expression invariantly, you get this formula. And you can see that, again, the components here are growing without bound as p becomes a highly boosted vector. Okay. Now, this is not completely formal. This actually has experimental consequences, and I'd like to describe one. So let's think about top quark decay. So the top quark is a very unusual quark. It's the heaviest known quark. The top quark is heavier than the W boson. And so whereas with all the other quarks, you decay through a virtual W boson into a multi-fermion final state, for the W boson, you decay to a real W boson. And the decay process is T goes to B plus W. The top quark has a mass of 170 odd GeV, and the W is 80 GeV. The bottom is relatively light compared to that. So just for the point of principle, you can ignore the bottom quark mass. Actually, it's a pretty good idea, pretty good approximation, to just ignore the mass of the bottom quark and treat the bottom quark as a left-handed chiral fermion. Left-handed because this is a charge-changing weak interaction. So let me do that. Here's the matrix element. So left-handed spinors, the W polarization. This is totally well-defined. You just basically plug in the numbers and you compute it. And I'll give you the answers on the next slide. It's nice to see that one can actually measure the things we're talking about. So here's an example of a top quark, anti-top quark reaction at the LHC. We're looking at the Atlas detector down the barrel of the detector. So the protons are coming into the blackboard here. Hopefully not into this blackboard. You can see on this side an electron. So in Atlas, there is a tracker in here. The green is an electromagnetic, the green is an electromagnetic calorimeter. The red is a hadron calorimeter. You can see that the hits are all in the electromagnetic calorimeter, so this, and there's a track pointing to it. So this is an electron. Here there's a jet. The jet has a B tag in the way that I described in the previous lecture. There's a displaced vertex. On the other side, it's a little harder to make out, but there are 3 jets. Actually, if you project the energy deposition onto a plane, you can see it more clearly. Unfortunately, Atlas published this with the event upside down. So here's the electron, here's the B jet, which is here. The top is the bottom, but you see there are 3 distinct piles of hits corresponding to the 3 jets from the W decaying hadronically and the B quark. And I think one of those, yeah, here we go. So this is a blow up of that picture. And again, this object here is B tagged. So its top goes to B plus W with a leptonic W decay here and a hadronic W decay here. So by measuring all the momenta in this event, you can actually completely reconstruct the TT bar production, and you can then boost to the frame of any top quark and measure all the angles in this event. So now we can talk about the angular distributions of the decay. An interesting, so let's choose a coordinate system where the top quark is at rest. We'll think about the W moving in the 3 direction, and the top quark spin is in some arbitrary direction described by a 2-component spinor called Xi. And here are the spinors that go into that formula. And the sigmas are some matrices that you can find in chapter 3 of my book. So you just plug in everything, and here's what you get. The W, the B is always left-handed. The W can be left-handed, right-handed, or having this longitudinal polarization state, the extra one. It turns out that the right-handed polarization, it's actually, the matrix element is 0. For the left-handed polarization, it's given by this formula. And for the W0, when you evaluate the sigma dot epsilon, because of this extra factor of P over MW, when the W is boosted, there's an extra P or E over MW here. And then if you take the ratio of the amplitudes, you get something that's of this size times an extra factor of MT over MW. Okay, well this is interesting. It says that that extra polarization state, which actually we hoped wouldn't even be there if it were a regular vector boson, is actually enhanced in W decays. And by exactly the factor that I showed you, the extra factor that's in this longitudinal polarization. And so if you write, so here are the actual decay widths. Again, there's an extra factor like that. And if you calculate the probability that the W comes out in the longitudinal polarization state, here's the formula. This is that enhancement factor again. It turns out to be 70%. So most of the top decays go to this unwanted, if you like, polarization state of the W. The reason for that is it's obvious, because the polarization vector is bigger because of the physics that we just described. Okay. Well, is this correct experimentally? Well, now you can test that, because I showed you that if you can measure the angles, I showed you how to measure the angles in a top decay event. So in particular, you can measure the W decay angle. That is the angle between the W in its rest frame and a decay lepton. And it turns out that there's a very simple distribution, that if the lepton goes forward, it's a right-handed electron. If it goes backward, it's left-handed. And if it's central, it's the longitudinal. And here are the angular distributions that you can use to fit. Now, you have to be a little careful, because if you have a W that's boosted and the lepton goes backward, it might be too low energy to see. So you have to fold this with the acceptance of the detector. So the people who originally measured this, the CDF experiment at the Tevatron, took that into account. Those simple distributions turned into something more like this. And the prediction of this theory is mostly the green, no red, and a little of the blue, making a distribution that looks like this. And as you see, the data is a very nice fit to that distribution. Of course, this has been redone at the LHC with much higher statistics, and it's even more beautiful. So once again, this is that curve visualized in the CMS detector at the LHC. And these are some background processes that one can estimate, and you can see that the sum of them is just beautifully represented by the data. So whatever happened to that longitudinal polarization state, the calculation that we did is actually correct, that it is produced more copiously than the ordinary polarization states of the W, and it directly reflects the fact that the polarization vector is proportional to P over M, which becomes large when the W is boosted. Oh, by the way, let me call to your attention that I never used Higgs or spontaneous symmetry breaking or any of that stuff in this argument. I just wrote down the formula for a massive vector boson. I computed it, and this is what I got, and it agrees with experiment. Okay, but it's weird. Because why would this be true? Well, it turns out that if you say, well, secretly, that extra polarization state of the W came from the Higgs boson, it's much easier to understand this. So let's work that out. So if the extra polarization state of the W is actually borrowed from the Higgs sector, maybe when the W is at rest, it's a little hard to tell which polarization state is which. But when the W is moving more or less at the speed of light, then the transverse polarization should be the old states, the original states, and the longitudinal polarization should be the one that got eaten from the Higgs sector. And we would expect a formula like this, that the matrix element for the T going to B W0 should approach the matrix element for T going to B and the Goldstone boson from the Higgs sector that was eaten when the W boson becomes massive. So let's work out this formula. Now, the transverse W's couple to the top quark with the strength G, the universal strength of the weak interaction. But the Higgs boson doesn't couple to the T with the strength G. It couples to the strength of the Yukawa coupling that gives the top quark its mass. And you remember I told you in the previous lecture that the alpha W is 1 over 30, but the alpha Higgs is 1 over 13. It's more than twice as large. So you put in the various numbers, including the right square roots of 2. The amplitude should be enhanced by yt squared over g squared, which is this in terms of the masses, which is exactly the enhancement factor that we found in the previous argument. So if you postulate a generic massive W boson, you get this answer. It agrees with experiment, but it doesn't make any sense. But if you say the W got its mass through the Higgs mechanism, then actually you can use this formula. You get the same answer, but now you see why it's bigger. It's bigger because the top quark is more strongly coupled to the Higgs sector than to the weak sector. OK. Now, it turns out that within the gauge theory, there's actually, the formula I wrote is actually a theorem. It's called the Goldstone boson equivalence theorem, originally proved by Cornwall, Tiktopoulos, and Vianakis. Here's the general statement of the formula, that if I have x going to y plus a longitudinally polarized W, that's equal to the corresponding amplitude to make the Goldstone boson up to corrections of order mw over EW. That is, it's true in the high energy limit. If you'd like to see a very elegant proof of this formula, but I should say not for beginners, you should look in the paper of Chanowitz and Gaillard, which is cited here. These guys use all the equipment of spontaneously broken gauge theories, but it's a very elegant proof. Okay. Now, just to show you that this is a little more non-trivial, let's look at another example, which is E plus E minus to W plus W minus. So I'd like to estimate first the cross-section for E plus E minus to W plus W minus, and then think about it in terms of this Goldstone boson equivalence theorem. So here's a way to estimate that. Let's first write down the cross-section for E plus E minus to a pair of scalars. And it's equal to this quantity. It's basically just this simple Feynman diagram. Okay. So if you compute that Feynman diagram, it's a photon exchange, so there's a 1 over s, and the rest is just the usual momentum structure. Now, if we have W bosons, the W bosons are polarized, so the polarization vectors have to be added to this formula. And I think a very reasonable proposal is just to multiply this formula by the Lorentz product of the two polarization vectors. But this leads to problems. So this is the obvious thing that you would write down. But this leads to problems, because remember that if I have a longitudinal polarization vector, this is proportional to k minus over mw, and this is proportional to k plus over mw, and k minus dot k plus is s over 2. It's the square of the center of mass energy. So you get this factor, which is the square of the center of mass energy over mw squared. And that already actually is a factor that would cause the cross-section to rise fast enough to violate unitarity bounds. And actually, then you have to remember that this is the amplitude, so you square it, so it's actually twice as bad as you thought. Okay. So then the question is, what does experiment say? Is this huge enhancement of this W plus W minus cross-section there or not? Well, before I tell you what experiment says, let me tell you what the Goldstone boson equivalence theorem says. The Goldstone boson equivalence theorem tells you that this quantity goes asymptotically at high energy to this quantity, which is just ordinary scalar production. So that extra enhancement factor basically can't be there. There are some different order 1 numbers, but the big enhancement can't be there. The cross-section only has a 1 over s, and it perfectly respects unitarity. At least that's the prediction of a gauge theory. If you had a non-gauge theory, if you just tried to basically stick a mass onto the W boson, you might be totally in the soup. Okay, now let's ask what oh, and by the way, if you interpret this, now, then you could ask the question, well, this answer is very different from the one on the previous slide. So how could that possibly happen? Because what I wrote down on the previous slide was a very reasonable proposal. And the answer is, it's very tricky. If you compute this in the standard model, there are 3 Feynman diagrams. So this is the one that I tried to estimate, but there are 2 more. And when you calculate these diagrams, they have the potential to cancel in the high energy behavior. And that cancellation depends critically on what you assume for the 3 vector boson vertex. And you folks all remember that in Yang-Mills theory, the 3 vector boson vertex has a structure which is predicted by gauge invariance. It's a very particular structure. And actually what happens is that by virtue of having these vertices be exactly the Yang-Mills vertex, there's a cancellation that cancels the dangerous term that I estimated here. So that's something that's very special to the gauge theory structure. Okay, now what does experiment say? Well, this process was measured at LEP2. Again, I validate that by showing you some event displays. This is E plus E minus to W plus W minus tau nu. So here are 2 jets. This is actually a pion from the tau decay to pi nu. And then you can reconstruct the mass of this 2-jet system. It turns out to be 80 GeV, the mass of the W. Yes.
In the electron-positron annihilation,
yes.
sometimes photons are expected.
Yes.
Here, we get the boson. The difference in the experiment, is it just related to the energy in compared to photon production? Just energy of the beams are different, or some other extra constraints are present?
Oh, so you remember in the previous lecture I talked about this a lot in relation to the Z resonance. So there, the Z is a very sharp structure. And the photons basically come out forward along the beam direction. They affect the energy of the electron and positron, and they affect the shape of the resonance. So here, the same thing occurs. When the electron and positron annihilate, they emit some photons. That affects the shape of the cross-section. But here, it's a smooth structure, so it's a very small effect. It's a 10% effect. For the Z, it's a 100% effect. Here, it's a 10% effect. OK, here's another event display. This is both W's decaying heteronically, and then the Opal experiment here sorted that out into 4 jets. And the 2-jet invariant masses, again, are 80 GeV. So it's W pair production. OK. So now the big question is, what does the cross-section look like as a function of energy? So would anyone like to take a bet? You all know how this is going to turn out. Here's the answer. This is the standard model prediction. This is the data, the average of the 4 LEP experiments. There is no big enhancement of the cross-section as you go to, even, this is very close to threshold. There's the threshold at 160. It's smeared out a little by the effects we were just talking about. These are some people who did the one-loop corrections. The data is in very good agreement with that. If you leave out one of those 3 diagrams, you get the red curve. And if you only include the T-channel diagram, if you only include this diagram, you get the blue curve. So you can see that there's really a dramatic cancellation between the diagrams, which requires the Yang-Mills structure of the vertices. OK. OK, so I hope I persuaded you now that it has to be a Yang-Mills theory. And in order for the W's to become massive and the Z's, there has to be spontaneous symmetry breaking. So what's the deal? What is the mechanism of this spontaneous symmetry breaking? Why does it occur? So here, I think you can just say, well, the standard model allows this to happen. It happens. We're happy. We go home. And I strongly encourage you not to take that position. Because I think in physics you always need to understand at every level why things happen. And the explanation for this spontaneous symmetry breaking in the standard model is just not a very good explanation. So let's talk a little about that. Okay. So here's the complete explanation for SU2 cross U1, spontaneous symmetry breaking in the standard model. There is a field called phi, which is a doublet under SU2. It has the quantum numbers of SU2, isospin a half, and hypercharge a half. The standard model is a renormalizable model, so I wrote down the most general renormalizable potential. Here it is. Now I assume that this parameter mu squared is less than 0. Then the potential has a shape like this, rotated around the axis, of course, with an asymmetric minimum. And that then, once this minimum occurs at a value of phi equals 246 GeV, then all the rest of the experimental predictions that I've given you in these lectures follow. And about that you can be partially happy until you ask the next question, which is, why did I assume that mu squared is less than 0? I could equally well have assumed that mu squared is greater than 0, in which case the potential would have a completely different shape, the W and Z would be massless, and the world that we live in would be like another universe. Okay. So unfortunately, the answer to this question cannot be addressed within the model. It's just an assumption of the model that mu squared is negative. Okay, well now you can try a little harder. Maybe radiative corrections would help us understand why mu squared is less than 0. So you compute the first order radiative corrections to mu, and the largest effects are given by these diagrams, one involving the Higgs self-coupling, lambda, and one involving the interaction with the top quark, which is proportional to yt. Please notice that both of these diagrams are divergent. So I've just put a cutoff here. The coefficients, I know what they are. The cutoff, I don't know what it is. It could be the Planck scale, the Gut scale, 100 TeV. Take your guess.
I don't understand why your loop use top box.
Sorry?
Your loop use top box.
Sorry, Higgs boson,
And yes.
top quark, Higgs boson. It's the Higgs self-energy.
I know, but we have Barton or something.
Oh, but this is the top quark Yukawa coupling. It's proportional to the top quark mass squared. There are additional contributions, proportional to MW squared, M neutrino squared, okay, all those things. But this is the biggest, these are the biggest contributions. These are the, well, they're not, I mean, there are many one-loop diagrams. These are the numerically largest one-loop diagrams. Okay. So please notice, first of all, these diagrams are divergent. Now, in a normalizable theory, that's not supposed to bother you. You just sweep them under the rug by letting mu equal to the bare value of mu, and you cancel the divergences. Although that's an odd thing to do. If lambda is the Planck scale, you have to make a cancellation in the first 30 decimal places. The other thing is that this correction is positive and additive. This is negative and additive. So depending on which correction is really dominant, the mu bare can be very positive and canceled by this term so that mu squared is a little negative. Or if this term is dominant, it could be the other way around. So actually, there really is no way to predict the sign of mu in this theory unless you have an understanding of some deeper theory that leads to this theory. So that's what we've got to look for. In particular, it's a very attractive statement that the reason that mu has this value is because these diagrams are canceled by some other diagrams, but those necessarily involve new particles. And if mu has a value of about 100 GeV, those new particles should be at the scale of a few hundred GeV or a TeV. So maybe we really should be strongly engaged in looking for new particles that have TeV energy that we can add to this calculation so that eventually it makes sense. This doesn't make sense. Now, this problem is not new to high energy physics. There are many, many examples of spontaneous symmetry breaking in nature. Probably the most familiar one is superconductivity, which is illustrated by this demonstration that probably most of you have seen in your physics classes. Superconductivity is a property that electron pairs condense and form basically an indefinite number of pairs in a metal. That condensate then flows through the metal frictionlessly, and that frictionless flow allows zero resistance and many other interesting effects, like the Meissner effect, the repulsion of magnetic fields, which is illustrated here. It was discovered in 1911 by Kamerlingh Onnes, who was basically the only person in the world who could make a cold enough temperature that a metal would go superconducting. And he kind of had the monopoly for 10 years. Eventually, in the 30s, there were many other people studying this. And in particular, in Moscow, Kapitsa had a big effort on the experimentation of superconductivity. Nevertheless, no one could figure out why it occurred. And actually, the explanation was not understood for another 45 years. Now, in 1950, Landau and Ginzburg decided that they would, even though they didn't understand why superconductivity occurred, they would write a phenomenological model of superconductivity, which is known now as the Landau-Ginzburg equation. And it's an effective free energy, which is of this form, which you will notice is exactly of the form of the standard model Higgs potential. And the reason is that it's the same argument that leads to that. You write the lowest number of fields, the simplest polynomial, that has the phenomenon of spontaneous symmetry breaking. A of t here is a constant which they just postulated would be positive at temperatures above the superconducting transition and negative at temperatures below the superconducting transition. Now, this theory is one of the most successful theories ever in physics. It explains the form of the phase transition, the fact that there's a discontinuity of the specific heat, the existence of what are called type 1, type 2 superconductors. It explains the Meissner effect. It explains something called the critical current, which is to say if you try and pump too much current through a superconductor, it becomes normal. Many other features of superconductivity are described by this equation. And yet, people knew that it was not a phenomenological description, because somehow we knew that superconductivity had to come out of atomic physics, the physics of electrons and nuclei and solids, and this was not it. And actually, it took 7 more years until Bardeen, Cooper, and Schrieffer developed the idea of electron pairing, the so-called Cooper pairing, which then gave a true microscopic explanation of superconductivity. So I think this is a nice lesson for particle physicists. We are now in the Landau-Ginzburg stage of our understanding of the standard model. And there is something beneath it. Certainly, it is something that I believe very strongly. There's something down there that would explain why the Landau-type Lagrangian that we work with now is the correct thing to write. The only problem is that in superconductivity, we knew that electrons and nuclei had to somehow supply the ingredients. For particle physics, all we know is that those ingredients are not in the standard model. And so we have to discover some new particles, and we haven't discovered them yet. So until we do, we're just guessing or speculating, or maybe with more or less wisdom about what should be there. So on general principles, these must be some new particles and fields not in the standard model. We only know that we have not discovered them yet. They are out there, and we need to find them. Okay, here's a crazy example that I like to show to particle physics audiences. This is something called a pneumatic liquid crystal. There's some obvious symmetry breaking here, which has to do with the molecules in the crystal lining up along a preferred axis. The reason they can do that is because the molecules look like this. They have actually a preferred direction, which can line up at a sufficiently low temperature. This is a pretty involved mechanism that nature made to have spontaneous symmetry breaking in a fluid. And I think we shouldn't prejudice ourselves by saying that the real explanation for the symmetry breaking in weak interactions must be simpler than this. It might even be more complicated. Okay, so there is, of course, an obstacle to creating a theory where you can predict the existence of spontaneous symmetry breaking. The problem is that you have to predict the sign of the Higgs mass term, which means that you have to be able to compute the sign of the Higgs mass term. And the sign of the Higgs mass term is typically an infinite quantity unless it's protected by some symmetry. So probably what we need to do is to find a model where when some symmetry is imposed, the Higgs mass is 0. And then you can't turn on the Higgs mass unless you break that symmetry. And then if you break that symmetry a little, there'll be a radiative correction, and then you can compute that, and you see whether it's positive or negative. And if it's positive, then you throw your theory in the wastebasket. And if it's negative, you publish in the Physical Review or wherever. So now the problem is that there aren't many symmetries that forbid the mass of a scalar particle. I think I like to tell people in my textbook there are no symmetries discussed that disallow the term m squared phi dagger phi. Okay, it's Lorentz invariant, it's a scalar, it's invariant under all the global symmetries. There are a couple examples that come to hand. One is supersymmetry, where using supersymmetry you can forbid such a mass term. And then when you break supersymmetry, it gets turned on by a radiative correction. The other is if you consider the Higgs as a Goldstone boson of some higher symmetry breaking. And actually, both of these approaches are used to make models of, kind of predictive models of electroweak symmetry breaking. The other way you can go is you can go the route of BCS, which is to say the Higgs is composite. There's some binding interactions that bind some constituents, and then we would have a composite or strongly interacting Higgs. And I think most approaches to this problem fall into one of these two categories. There's some completely outside it, but most of the things we'll talk about are within one of these categories or another. Now, some guidance is given by the following statement, that you remember that in the previous lecture I made a big point of the fact that the standard model obeys the relation mw equals mz times cosine theta w. So this is a relation that actually is not true in many theories of physics beyond the standard model. And so it turns out to be an interesting kind of fixed point if you try to extend the standard model to make sure that this relation is true. In the standard model, it was true because we just computed the masses and that's what it turned out to be. But there's actually a deeper way of understanding it, which I'm now going to explain to you. So here's the standard model vector boson mass matrix in terms of the SU2 and U1 gauge bosons. And you see that the form of it is very kind of easy to understand. The SU2 part is completely symmetric. These three elements are equal. Then we construct the model so that the photon is massless. So there must be a 0 eigenvalue. So I've then given g squared here. I filled in these elements in such a way that there's a 0 eigenvalue here. And now the matrix is uniquely determined. And now if you calculate the z mass here, you'll get, here for the w mass you get g squared. Here for the z mass you get g squared plus g prime squared, the square root of that. Then you get the relation mw equals mz cosine theta w. So if we can somehow guarantee that these three elements are equal, and also that the photon is massless, then we're actually done. And there are lots of theories that can do that. The symmetry among these is called custodial SU2 symmetry. It's an unbroken global symmetry of the theory, which stays unbroken after the gauge symmetry is spontaneously broken. So an interesting question is, what kinds of models have custodial SU2? So let me give you a little catalog of them. So this is where I promised that I wasn't going to really explain the models. Oh, this is the standard model. But when I go on, I'm not really going to explain the models. I'm going to catalog them. And those of you who are interested, we can talk privately about some deeper explanation. So first of all, why is custodial SU2 a symmetry of the standard model? Well, there's one Higgs boson. Let's write it in real coordinates. Phi squared is actually phi 0 plus phi 1 plus phi 2 plus phi 3. If I give phi 0 an expectation value, that preserves the SO3 symmetry among the other components. That would be the custodial SU2. And so we get this equation in the standard model. But there are many other models that give this, and they have an interesting variety. Let's go through them. First of all, there are models with 2 or multiple Higgs doublets. And so to think about that, let's think about the fermion-Higgs couplings of the standard model. So I'll write the left-handed fermions in doublets, the right-handed fermions in singlets. These are the terms that you write down in the standard model for the Yukawa couplings. And here I wrote phi 1, phi 2, and phi 3. So there are 3 Higgs bosons. And in particular, I could put 9 Higgs bosons. I could put a very large number of Higgs bosons in here. In the standard model, we take the simplest choice, that there's 1 Higgs boson. But we don't have to do that. It turns out that if you put a Higgs boson in each term and make that independent of the generation labels, then you preserve the custodial symmetry, and again, you get this relation. You can have more or less as many Higgs bosons as you want, as long as you preserve the generation-independent structure. In the standard model, we have 1. We set phi equal to phi 1, phi 2, and phi 3. But we could as well introduce separate fields. For example, 1 for the up quarks and 1 for the down quarks. An example of a model like this is the supersymmetric extension of the standard model. Now, remember that if I were to use 1 Higgs field, I can put phi 1 and phi 2 to be the same Higgs field here. And that Higgs field would have hypercharge plus a half. But over here, because it's U, this has to have hypercharge minus a half. And in order to do that, I put phi equal to phi 3 star. However, in supersymmetry, that doesn't work. If you try and identify the same field with a given field and its complex conjugate, then you destroy the supersymmetry transformation. So in supersymmetry, you have to have at least 2 Higgs fields. And actually, you have an even number, so you can basically, again, have as many as you want, provided that you always introduce the Higgs field into the Lagrangian as phi and not phi star. Now, maybe I should say that supersymmetry models have a very rich phenomenology, which I'm not going to describe in these lectures. And this change in the nature of the Higgs boson is only one of many potential ways of discovering that the standard model is extended to a supersymmetric model. The most interesting ways are the discovery of the supersymmetric particles. But of course, that hasn't happened yet, so let me now turn the page. Okay. So here's another model. This model involves higher representations of SU2. It's called the Georgi-Mahacek model. Here, the X is a matrix of Higgs bosons with this structure. This is for I equals 1. So this guy here, the doubly charged Higgs, has a weak isospin, SU2 quantum number I equals 1. Actually, there exist these models for any isospin. And if you set up the Higgs structure in the right way, you're always actually guaranteed to have a custodial SU2 that gives you this relation. A more interesting model is a model called Technicolor that was introduced by Steven Weinberg and Lenny Susskind in 1978. In this model, you really go to the with the BCS idea. So we postulate a new strong interaction theory, which is just like QCD, except that it becomes strong at an energy scale instead of 100 or a few hundred GeV, it becomes strong at a few TeV. In that theory, we have, let's say, two massless flavors, U and D, and we would have a chiral symmetry, SU2 cross SU2. If these things have zero mass, because we haven't broken the electroweak symmetry yet, we put in the left-handed particles in doublets, just as in the standard model, and the right-handed particles in singlets. If we then have the chiral symmetry breaking that we have in QCD, if that same phenomenon occurs in this theory, this SU2 cross SU2 gets broken to the diagonal SU2, which is the symmetry called isospin in QCD. So the analog of isospin symmetry here would be the custodial SU2, and again, it would preserve this mass relation. The formula for the W mass is something like this, where F pi here is the analog in the new strong interaction theory of the pion decay constant. I know at least one of you now knows what the pion decay constant is. Here, the pion decay constant plays the role of the Higgs expectation value, so its value is 250 GeV, and that puts the rho mass, the resonance masses of the strong interaction theory, at about 2 TeV. So this is a possible strongly interacting Higgs model that's actually totally consistent with a lot of our knowledge. Actually, this specific model is actually not consistent with our knowledge. It's excluded by the measurement of this S parameter that I referred to at the end of the previous lecture. And actually, the worst thing about this model is that it contains no light Higgs boson. So it's dead. But there are analogs of it that survive. Yes, yes, yes. There's a strategy called little Higgs, which was developed by Akani Hamed, Cohen, and Georgi, and other people. Here, we're going to use the idea of Higgs as a Goldstone boson. So we introduce new strong gauge interactions, let's say at 10 TeV. Those break a symmetry. In this case, a chiral symmetry, SU4, is broken down to SO4. If you do the counting, this has 15 generators, and this has 6 generators, so you get 9 Goldstone bosons. If you ask, SO4 is actually, the Lie group is SU2 cross SU2, so we can classify things under SU2 cross SU2, and it contains a half, which is the two-complex doublet 4-dimensional representation that the Higgses live in the standard model. Again, we can try to introduce some potential. We can gauge this SU2, but the other SU2 exists as a global symmetry. If we can give an expectation value to the Goldstone boson, I'll tell you how to do that on the next slide. Again, this is broken to a diagonal SU2, and again, it preserves this relation. So in these models now, we have increasingly more complicated structure that's beyond the standard model. But as long as we focus on this, we keep control over it in the sense that they don't make large corrections to what we know. And finally, there's a model called holographic Higgs, which is due to these people, Agasha, Contino, and Pomerol. Here you introduce extra dimensions. So I introduce a 5th space-like dimension of space-time. I have a bounded interval in this 5th dimension. This setup is very similar to what's called in string theory the ADS-CFT correspondence. How many of you know what that is? Yeah, there's some string theorists here. You guys explain to the others what that is. I'm not going to. In particular, the 5-dimensional theory with gauge symmetry G represents, through this correspondence, a strongly interacting theory in 4 dimensions with global symmetry G. So what these people do is they choose G equals SO5. They break this using the boundary conditions at the boundary of this 5-dimensional space to SO4. This produces basically massless particles equal to the gap between these two groups. So there are 10 minus 6 or 4 massless bosons. And again, the SO4 is SU2 cross SU2. And these 4 bosons turn out to be in a half, which again is the correct representation to be the Higgs boson of the Standard Model. And then in both of these setups, in holographic Higgs and in little Higgs, it turns out that the Higgses are basically Goldstone bosons. So at the stage that I've described, their potential is exactly flat. However, when you couple the top quark to this structure, that breaks the symmetry so that radiative corrections generated by top quark loops can cause this potential not to be flat, but to have small curvature. And in particular, it generates, in both cases, a finite mu squared term. And then by direct computation, you can actually compute in both cases that mu squared is negative. And so the theory dynamically generates the spontaneous breaking of SU2 cross U1. Okay. Well, now I've given you a huge variety of possibilities for how to answer the question which I posed in this lecture, namely, what is the explanation, what is the dynamical mechanism for breaking the electroweak symmetry? I've just made a list of theories. It almost seems endless. So the next question is, how do we figure out which of these, if any, is the right answer? And to do that, we need more experimental data from particle physics. So there are 2 approaches. One is that all of these models predict new heavy particles. So we should go to the LHC, or maybe other sources of high energy particles, and look for those particles. Unfortunately, up till now, no new particles have been found, but it doesn't mean they won't be found tomorrow. And actually, the study of these searches is really interesting. People have been extremely ingenious in looking for all these different types of new elementary particles. Unfortunately, that's the subject of a whole different course, which I'm not going to give, although you can ask me about it. I'll be around next week. The other is that all of these models predict differences from the standard model predictions for the couplings of the Higgs boson. So since we actually know where the Higgs boson is, we could try and look at it carefully and see whether it exactly follows the predictions of the standard model. And if not, that would be a clue into what lies beyond. And so the next 2 lectures, which will be given, I guess, tomorrow morning, will discuss that program. What does the standard model predict for the Higgs boson? What have we measured? Is that sufficient to tell us something about this? And if not, how do we go forward? So I'll see you tomorrow morning, and we'll talk about that. Thank you very much. Okay, yeah. Yes?
You know, a theory claims that the high energy limit, the lambda of 10 minus, which means the Higgs potential will be unbound.
Yes.
What do you say?
Well, let me explain the statement first, and then we'll talk about its implications. This is a theory, I must say, I'm not particularly fond of, but many people are interested in it. So the Yukawa coupling, YT, renormalizes lambda through a diagram that looks like this. So this is one diagram. So you have Higgses on the outside, and top quarks going in a loop. Okay. And then this diagram and some others that you can draw renormalize the Higgs self-coupling. Now, it turns out that renormalization, d lambda d log q, is negative yt squared over 16 pi squared. There's some factor of 3. I forget what else is there. But it's negative in the direction that as q gets larger, the lambda gets smaller. And by the way, it's an additive thing. It's not a multiplicative thing. So you add a negative contribution. of course, it's on a logarithmic scale. So it takes a long time, or you have to go to very short distances or high momenta in order for this to be effective. So usually we draw the Higgs potential looking like this, where this is 250 GeV. But to describe this phenomena, you have to use a somewhat different scale. So by the way, this is in the standard model. This is the prediction of the standard model. To describe this phenomena, you have to use a somewhat different scale. So let me do that. This is terrible. Okay. So 250 GeV is here. The potential that I drew over there is here. Okay? Then it goes way up, and it comes way down. And people debate about where this point is, because we don't really know yt very accurately. And we're integrating over logarithmic scales in momentum. But if the central value for the standard model parameters puts this at 10 to the 11 GeV, and then it just keeps going down. Okay. So the fate of the universe is now the following. Eventually, so we now live here. Eventually, we will tunnel from here to here by the creation of some vacuum bubble. The expected time for tunneling, given these parameters, is 10 to the 500 years. But when that happens, a vacuum bubble will be spontaneously produced. It will expand at the speed of light. Nothing can expand at the speed of light, but it expands so fast that by the time we see it coming and the nerve impulse goes from our eyes to our body, it'll be too late. It'll overwhelm us. And then our whole area of the universe will be plummeted into whatever vacuum is down here. So that's the eventual fate of the universe. But don't worry, it's not going to happen for another 10 to the 500 years.
This energy is higher than this. So
Sorry?
after inflation, your reverse inflation, after the inflation, energy is much higher than 10 to 11.
Oh, yeah, you have to figure
It
out.
will collapse immediately.
Well, then we couldn't be here. Then the standard model would be wrong. But it turns out that there are ways to, like, the reheating after inflation, maybe it's only up to 10 to the 10 GeV. So we don't actually get here. And then there's also a lot of uncertainty in this number. So within the uncertainty in the top quark, now I would say plus or minus 2 GeV, maybe 3 GeV. Okay. Some people say we know the top quark mass to half a GeV. I just don't think that's correct. I think this is probably a reasonable error for the top quark mass. So within that range, this can be anywhere from 10 to the 10 all the way up to the Planck scale, 10 to the 18. And of course, if this comes in just at the Planck scale, that's very interesting. So there's a certain literature in which people look at all these possibilities. But I hope I answered your question. Okay. Now that we've discussed the death of the universe, does anyone else want to ask a question?
Still another question.
Yes.
Your lecture, you didn't mention about the neutrino.
Sorry?
The difficulty of neutrino, neutrino mass.
Oh, I didn't mention neutrino mass.
Yeah, yes.
Why is neutrino mass a difficulty?
Neutrino has mass.
Yes.
But you didn't mention that.
Oh, yeah. Well, it's not hard to add neutrino mass to the standard model, right? One way to do it is just you add a Yukawa coupling for the neutrino. It has to be very small. It has to be very small. It's 10 to the minus 12. But it's perfectly allowed. Another thing that you could do is you could add a dimension 5 operator, which has 2 Higgs boson fields in it, and that would give mass to the neutrino. And then people have more elaborate theories of neutrino mass that go beyond the standard model. So, you know, I could give a whole lecture on this, but I'm not going to. So let's discuss it offline. Oh, and yeah, and Yasmin Farzan is not here to annoy me about this, so I don't have to talk about it. Okay. She's a big advocate. She's a big proponent of models of neutrino mass. Hello. Anyone else? Yes?
Does any of the other Higgs models that postulate additional Higgs field?
I'm sorry?
Do any of them connect to the complex or any efforts of modeling?
To the what field?
Inflaton.
Oh, well, in this case, actually, if you have lambda go to 0 at the Planck scale, the theory that you get here, I shouldn't have drawn it this way, this becomes very flat. So you can actually have the Higgs as an inflaton here. And Shaposhnikov has written papers about this. And there's a way to have a reasonable, so this is already lambda's negative. So what you can imagine is a potential that looks like this, and it's within the parameters of the standard model. And then here, the Higgs is an inflaton. And then it eventually rolls off and becomes the standard model. So there's a literature on this. I think if you look at up the papers of Shaposhnikov, you'll find a lot about this. That's not the only theory of the instanton, but of the inflaton, but it is one. And it specifically requires this physics that I was kind of making fun of a moment ago. Okay. Anyone else? Okay, well, as I say, I'll make the lecture notes available. I'll be around. And let me know if I can answer any more questions. Thanks a lot.